In this video here, we're going to take a look at direct impact and Newton's law of restitution. Now, we can solve problems involving the direct impact of two particles by using the principle of conservation of momentum and Newton's law of restitution. So, a direct impact is a collision between particles which are moving along the same straight line. And when the two particles collide, their speeds after the collision depend upon the materials from which they are made. Now, Newton's law of restitution defines how the speeds of the particles after the collision depend on the nature of the particles as well as their speeds before the collision. Now, this law only holds when the collision takes place in free space or on a smooth surface. So, obviously, for exam questions, these conditions will always be satisfied. But just so you're aware here, these two conditions here must hold for Newton's law of restitution to hold. Okay? So, Newton's law of restitution states that E, so we use E here to represent Newton's law of restitution, is equal to the speed of separation of the particles all over then, or divided by the speed of the approach of the particles. Now, the constant E, as I've just mentioned, right, is the coefficient of restitution between the particles, where E is between 0 and 1. Now, the value of the coefficient of restitution E depends on the materials from which the particles are made. So, in a perfectly elastic collision, E is equal to 1. So, the speed of separation is the same as the speed of approach. And hopefully, that should seem quite intuitive. And for the opposite situation here, this is when we have a totally inelastic collision. In other words, E is equal to 0. Now, in this case, the particles will coalesce on impact. And I'll show you an example of what this will look like very, very shortly. So to finish with here then, let's just take a look at direct impact and Newton's law of restitution visually. So the table below here should help demonstrate the difference between a perfectly elastic collision. Again, this is when E is equal to 1, and a totally inelastic collision. And again, this is when E is equal to 0. So I've got two situations here, before the collision and then after the collision. So for before the collision here, both situations are clearly the same here. So when we have a perfectly elastic collision, when E is equal to 1, and same again here for a totally inelastic collision, when E is equal to 0. So the difference here then is for after the collision. So for a perfectly elastic collision here, that is when E is equal to 1. Just notice here then that the particles will bounce basically off each other and go in the opposite direction. So it's traveling to the right here. On impact, it then travels to the left here. And then same again for this particle on the right here, it's traveling to the left. On impact, it then travels to the right. And this is for the situation then when we have a perfectly elastic collision. In other words, when E is equal to 1. So in the situation then, when we have a totally inelastic collision here, that is when E is equal to 0. As we can see then, what happens here is the particles will coalesce, right? In other words, they essentially just kind of join together. So for a totally inelastic collision, a good example to think about here is two balls of sticky plasticine. This would produce a totally inelastic collision because E would be equal to 0. And in that case then, the speed here is just simply 0 meters per second. Okay. In all of the situations, it's just V meters per second. So V, V, and V again here. Okay. And we can also use the principle of conservation of linear momentum together with Newton's law of restitution to solve problems involving two unknown velocities, right? And I don't actually have an example for that within this video here, but I will cover that in the next members video. So keep an eye out for that. I will leave a link in the description down below. So to finish with here, then let's just put all this together and work through a practice question. So let's just get started then with this practice question here. Now for this question, then what we've got here, two particles, so A and B, and they're traveling in the same direction on a smooth surface with speeds of 5 meters per second and 4 meters per second respectively. We're then told that they collide directly, and immediately after the collision, they continue to travel in the same direction with speeds of 3 meters per second and V meters per second respectively. So we're then given that the coefficient of restitution here between A and B is 1/4. All we want to do here then is just simply find V. That's this speed here, right? So this question here is a pretty straightforward application then of direct impact and Newton's law of restitution. Let's just work through it anyway, right? So to begin with here, let's just recall then that the coefficient of restitution here, that is E, so E here, is equal to the speed of separation of the particles divided by the speed of the approach of the particles, okay? So to save me writing this out in full here, I'll just write this as speed of separation over speed of approach, right? I do mean the full thing there, so speed of separation of particles all over the speed of approach of the particles, okay? So let's just write this down then. So speed of separation. So speed of separation all over, that's an M by the way. So speed of separation all over speed of approach. Okay. So in our case then, how do we find the speed of the approach here and the speed of the separation? So in that case then, E here is equal to, so let's just start then with the speed of the separation here. So for the speed of the separation, then clearly this is after the collision, right? So we're looking at these two speeds here, so 3 meters per second and v meters per second respectively. So for the speed of separation, then that would be this speed here, which is v, that's what we want to find, right? Minus this speed here of 3. So we get v minus 3. And that's all over then the speed of the approach here. So for the speed of the approach, then clearly this is for before the collision, right? Or before the collision, grammatically correct, there we go. So that is related to these two speeds here, so 5 meters per second and 4 meters per second respectively. So that would just simply be then 5 minus 4, okay? The first speed here minus the second speed, okay? And this here then is equal to the coefficient of restitution here, which as we're told here is 1 over 4, or 0.25 if you prefer decimal, but let's just keep it in exact form here. We get 1 over 4, okay? So clearly 5 minus 4 is just 1, so I've got v minus 3 over 1 is equal to 1 over 4, okay? Let's just write this down here. So v minus 3 is equal to 1 over 4. Good stuff. So we just want to solve for v here, right? So therefore v is equal to 1 over 4 plus 3. So if we get this over a common denominator here, that would be 12 over 4 plus 1 over 4. So that is 13 over 4. So 13 over 4. And if you want to give it a decimal, it's not necessary, but if you want to give it a decimal here, that would be 3.25. In this case here, don't forget your units as well, meters per second. Okay. And there we have it then. So like I said, a straightforward application here of direct impact and Newton's law of restitution. Either way, it is still good practice here. It just gets us familiarized with the concept here of the coefficient of restitution, right? So there we have it then. That gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on direct impact and Newton's law of restitution.